Hi, I'm Chrisferb, and I'm going to review how to do an ANOVA calculation with SPSS. It's just a single factor ANOVA, so it's pretty simple. It's not a MANOVA, which is multiple factors or multi. Okay, so I have SPSS open, and we have our data broken up into groups. So we have the outcomes from are essentially data in each group, and it says groups, and then it says 1, 2, 3, 1, 2, 3, 1, 2, 3, and we could actually reset this data, and we could do it as groups, and then the frequency of certain numbers, the data. But this is really raw, so we just have, it's essentially resetting groups 1, 2, 3, 1, 2, 3, and it goes down, and each time it has a value in there. And so what we're going to do is see how the relationship is between the essentially between the means of the groups. It's typically called ANOVA is typically the difference between the variances, but it's essentially the way we do it is it's also known as the means between the values. We look at the in-between and the within, and that's how we get that F score. So we'll take a look right here. Okay, I have the data all listed in, and now what we want to do is I'm going to go over how to do it. In SPSS, it's pretty easy to do ANOVA, where some of them are much more complicated. So I'm going to go to, let's see, Analyze, and then I'm going to go to Compare Means, and then I go to One-Way ANOVA. So we're doing one-way ANOVA. We're not doing the multi-factor ANOVA, which is MANOVA. So this is more of a type of ANOVA calculation that you might see in an intro to statistics class or something like that. Okay, so I select one-way ANOVA, and then I already have it on here. I'll back it up here, and I'll show you how this looks. Oh, let's go back. Okay, so we would open this up, and it says these are our columns right here. So for the first one, it's the groups, and I want to make that dependent because the actual data is within the groups. Okay, so we use the groups as the dependent list, and then for cars, which actually has all of our data in it, we are going to use that as our factor. Okay, so I have dependent list group, and then factor cars. Okay, and then we can take a look at a couple options here. It says post-hoc is one thing. Now there's a lot of different ways that we can do a post-hoc test. I'm actually going to check this. I was just looking at it a little while ago. Post-hoc analysis, what it usually does is it shows you where the differences are, and it gives you more information on this. But for what we're looking at, we're just going to see if there's actually a difference. So with the ANOVA, we're looking for usually the hypothesis statements are like this. It's all of the means in the groups are essentially the same within a certain range, of course, because it has to do with our level of significance. Or one of the groups is different than the others. So that's how we do this. So that's all that we're comparing, and it's the mu is equal to group 1, group 2, group 3, say. We could go on and have more groups. And then the alternative hypothesis is one of the groups does not equal the other ones, or something like that. Okay? So I have the significance level right in here. Now, we're not going to do this post-hoc test, so I'm going to do cancel right there. Okay. So let's take a look at options too. So descriptive, fixed, random. I'm not going to check any of these, and that's okay. I'm just going to do the basics for today, and I do okay. And that's it. It's not that fancy. So it says post-hoc tests are not performed. At least one group has fewer than 2 cases. So don't worry about that warning. We're not doing the post-hoc anyway. So just take a look at the ANOVA table that's listed here. It says sum of squares. And this is a traditional ANOVA table, the way that you would do this manually, if you've ever done these manually. You have the between groups, within groups, and total, and it says sum of squares. So you have the figure for sum of squares between groups, then sum of squares within groups, and it's that, and then total. And then degrees of freedom, 10. Degrees, now that's the between groups degrees of freedom. And then we have degrees of freedom within groups, that's 25. And then the mean of squares for each of these. And then the mean of squares calculates out, it's a fraction. One's on the between groups is on the numerator, the within groups is on the denominator. And then you put that out and you get the F-score. And the F-score that's listed here is the calculated F-score. So it's the calculated F-score. And then I want to show you one other thing. So what are we going to do with that F-score? How do we make a decision? So what we can do is we can look up what the critical value F-score would be. And in this case, we have to find it somewhere else. So I have a little table here that I took a screenshot from. And so with the F-score, it's always the F-score is calculated by our level of significance, our degrees of freedom 1, degrees of freedom 2. So degrees of freedom 1, which is across the top, is 10, and that comes from our DF between groups. That's 10. I'll go back. And then the second one is the degrees of freedom within groups, which is 25. So here we go. 10 is right here. So this is our V1. And then 25 is right over here. So this is a 5% level of significance, which is appropriate for this type of test. So, of course, it could be different. So the critical value F-score, if we're using the rejection zone method, would be 2.236, and our calculated F-score is 16.201. So if we imagine the rejection zones, the way that you can do this without using the p-values, we have this really low critical value, and then we have a really high F-score, so it's in the rejection zone. The other thing is, if we didn't have the means to look up what the critical F-score would be, we look at the significance level, and this is really low, because the way that SPSS works is if it's lower than a couple, I'm not sure, tens of thousands, I guess, then what it does is it actually just shows up as 0. Okay, so this is very low, but watch when I click on it. So I click on it, and now I have my mouse over it, and it shows that it is 1.4652 e to the -8, which means we move over the decimal point 8 times to the left, because it's -8. So what that means is the significance level, the calculated out p-value for what we're working with, is really low, and it's lower than it would be. It's lower than 0.05. It's lower than 0.01, because this is really tiny. So the take-home message would be we would reject in this type of scenario. And that is it. Thank you.